Network troubleshooting using Wireshark.
All right, let's see what happens. Internet's doing fine. Type in our command. Boom. So today I'm going to show you how someone within your network could perform a very simple but very effective denial of service on your internet connection. I'm also going to show you how to prevent that. So, full disclaimer before we get started, this is not something you do on a network that you do not own. This is not something you do maliciously, and I will show you as we go through this demonstration various safeties I've taken in order to prevent any sort of collateral damage from this. This is my network. It's a test environment that I've set up for this demonstration. The second thing I'll say is that I'm not just going to show you how to do it. You are going to learn. You're going to learn some networking, some network mechanics. You're going to learn a little bit about how the internet's delivered to your home. You're going to learn a little bit about security. Okay, so bear with me. It's just a lot of content, but stop, pause the video if you need to, ask questions in the comments, and let's go. All right, so here's the scenario. Let's take a minute to walk through it. First is your home network, which is represented on the right. This could be one or more PCs connected to a simple router. It could be a Wi-Fi router, a regular router. I've got my PC here that I'll be running some download tests from, and then also the script kiddie PC, who is actually the person who's going to be generating traffic and actually taking down the network. This is just a Linux machine that I use for testing. Now, what I need to explain to you about ISPs is as follows. When you have an internet service from a company, you get a certain speed, right? They tell you have, 60 megabit per second download and 10 megabit per second upload, or whatever it may be. It could be a gig, or it could be 150, whatever it is. This policy to limit your bandwidth is set not at your router here, but it's set within the ISP's network. Okay, they have policies on their routers to actually limit how much each customer gets based on how much they're paying for the service. Okay, and that means that you have an upload rate and you have a download rate. Now, generally speaking, most of what we do on the internet, whether it be streaming movies, whether it be downloading content from apps or from YouTube, whatever it may be, that's in this direction. That's the download direction, okay? So that's usually why there is a lot more bandwidth offered on the download direction than the upload, as most people are downloading more, most average users, okay? But the upload is still really important. And why is that? Well, even when you're downloading, you need upload. And I'll show you why. So I pulled up a very simple packet capture of a download, okay? In this scenario, my IP is 10.0.10.43. The remote web server is 170.39.230.155, and I'm downloading a file. If you're ever wondering how to tell what direction a TCP stream is going, there's some tools in Wireshark that'll do it, but just use your eye. Take a look at the length of the packets, okay? You can see here that the packets coming from 170 are 1500 bytes, 1500 bytes, 1500 bytes, and the packets that I'm sending back from me are 54 bytes. These are the acknowledgements, okay? So in TCP, when you're trying to download something from a server, say, it is a reliable protocol, meaning when you get chunks of data, say these 3 chunks or segments from that server, you as a receiver need to acknowledge that before the server is going to send you more. And that's really, really important here. Every time the server sends us chunks of data, look at these 2, we get an acknowledgement, and then more chunks, and then an acknowledgement. Okay, that's the pattern that's going to continue throughout this. If I scroll through, you can see most of these packets from the server are full-size packets, as we call them, 1500 bytes, between 1500 and 1520. And then you see these packets going back to the server saying, I acknowledge the data you sent me more. Now, what happens if you can't acknowledge the data back to the server? Well, what happens is the download stops. Because in reliable transport, in TCP, you can't keep transporting traffic unless the client acknowledges the data that's already being sent. Otherwise, the server will stop and say, hey, I don't want to send any more because I don't know if you've actually got it. That's not reliable transport. And that is the key to this attack. So going back to our scenario here, if I am, over here and I am downloading a movie and my direction of traffic is this, right? It goes from the internet to my PC from the server over here, okay? So over the internet to my internet provider's network, to my router, down into my PC. But say someone comes along and actually fills up the upload, meaning this upload here, they just overutilize it, completely fill it up. Well, what happens is you have problems getting acknowledgements from your PC to the web server. Because remember, for every few segments that are transmitted in this direction, you have to transmit acknowledgements, or ACKs as we call them, okay, back to the web server. So if I can't, as a PC, reliably transport ACKs back up to this web server, well, this data transfer is going to slow right down. And that's the crux of this, is that if you could actually clog up the upload of a home internet connection, or any internet connection for that matter, the download will slow down. And that's just a function of TCP mechanics, okay? So that's a scenario. We're going to show you what happens when, say, someone from, a malicious PC on your network generates enough traffic to fill up the upload, which will actually kill your download. So let's set up this attack. We got to answer 4 different questions, and this is going to teach you a little bit about what we're doing here. So before we answer the questions, the tool we're going to be using is something called nping. So nping is a utility that is widely unknown, but is part of the nmap utility. If you haven't heard or used nmap before, nmap is a very popular basically network scanning tool that allows you to discover hosts on a network, allows you to enumerate their services, find open ports, etc. Like nmap is incredibly popular. You can see here it's been in the movies. I think it was in The Matrix. But anyway, part of the nmap suite is a tool called nping. So nping is a packet generation utility. Now, there are nefarious uses for packet generation utility, like a denial of service, like we're going to show. But if you're a network engineer, you often need to have utilities like this installed in order to do your job and test out certain capacities and services, things like that. So in order to get nping, you just need to install nmap. It is available on Windows, Linux, and Mac. So whatever operating system you have, the syntax should be about the same, okay? So nping is the generator. So first question is, what kind of traffic are we going to use? Now, nping can generate ICMP packets, TCP packets, UDP packets. We are going to use ICMP, which is ping, okay? Why are we using ICMP and not any other type of traffic? And this is actually very key to this attack. And I want to show you this little graph down here. So this graph is of throughput and time. So basically the throughput as time goes on. And say this up here is the max upload rate of our internet connection. If we remember the diagram, that is this upload rate here of this pipe, okay? So this is what will happen when you use TCP. So if I try to upload a huge file through this and really kill it with TCP, TCP has something called congestion control. And what that means is that as the download rate goes up, right? It goes up like that, starts going exponential, hits the top, starts experiencing packet loss, and then what happens is TCP automatically backs off the rate. So you get something like that, okay? This is TCP congestion control. And the idea here is that TCP is trying to make sure that you don't max out whatever pipe you're going through, whatever connection you're going through, so that you have a acceptable user experience, right? So instead of blasting as much data as you can through this pipe, TCP detects that, say this is a 10 megabit per second connection, and then it'll actually back off. So for the purpose of doing a denial of service, that's not useful, right? Because you want to actually max out that pipe, and you actually want to have more packets in queue than the pipe can handle. So what you want with ICMP is stateless, meaning you just send the packets. You can, usually it's a request reply protocol, meaning you send the packets and you get a reply back, and then you send another packet. But you can also configure nping to just send the requests, right? So just send raw data and not wait for a response. And what that does, it allows you to do this. You can fill up the pipe. Let me get my custom pen. Fill up the pipe like boop, and then boop. You basically max out that interface. Okay, there's no dips up and down. It just tries to push through as much data as it can. That's actually a good segue into a concept known as queuing. Okay, so I'm going to make a little illustration down here to show you what I mean by queuing. Now, on the left, these are going to be pipes. I know internet's not actually a series of tubes, but we're going to use tubes because it's easy to see. So let's say this is a 1 gigabit per second connection, right? Say this is your PC, okay? And say this is a 10 megabit per second connection. And say this is your internet upload, right? That's to the internet. If you're sending a full gigabit per second of traffic to this pipe, right? You send this full volume and you're just going, pew, pew, pew. It's not going to get through, obviously. What's going to happen is by the time this data gets to this interface, there's too much data to be passed through at 1 gig speed. So 1 gig represents 1 gigabit of data is encoded and put onto the wire per second. That's what 1 gigabit per second means. But this interface here can only encode 10 megabits per second onto the wire. So what happens to the delta, the 990, megabits per second? What happens to that? Well, what happens is it queues up, okay? So there's something known as a queue that happens on the interface where the packets arrive and they get put into this queue, okay? And then as more packets arrive, there's more packets put into the queue and they line up all getting ready to go out here, okay? But you can imagine that if this just keeps sending data, well, the queue is going to overflow. And that's when you get something known as discards or drops, okay? So at a certain point, the queue can handle it, and maybe you get a burst of traffic. It fills the queue up, and then the traffic stops, so you can have time to send the data through the pipe. But if you get a constant stream and you don't get any relief, then you're going to fill up the buffers and you're going to start dropping traffic, okay? And that's what happens when you overwhelm a connection that is too small with traffic that just doesn't stop, right? You just fill up the buffers, and then eventually the buffers get worn out, or they get exhausted, and then you start dropping traffic. So that's a little bit about the theory about what kind of traffic and why we want to use something like ICMP for this. You could use UDP. UDP is very similar. It's stateless. I just like to use ICMP because I love ping. Second question is how much? Okay, and the simple answer to that is more than the upload bitrate. So when you're looking at your network diagram, if, for example, this is the interface here that you're trying to fill up and DoS, whatever traffic you're generating needs to be more than whatever the bitrate is here, right? In this case, it's 10 megabit per second. If it was another interface, say if another interface somewhere else in the network, you would just have to find out what that is, and then somehow target traffic to go through that interface with a higher bitrate than is being sent. Now, to where is a good question, right? We're talking about targeting. Now, you think about what happens when you generate this traffic from nping, and it's kind of like sending water out of a fire hose, right? You're just going to blast data at a very, very high rate at interfaces that can't handle them. Well, how do I make sure that this traffic is getting into this interface, right? And that comes down to routing. So if you look at this diagram again, on the left-hand side of the picture is the public internet. So on the public internet, we use IP addresses known as public IPs. And on the right-hand side, we have the private network, which is your network at home. And we use private IPs like 192.168 or 172.16. So if I want to generate traffic from here and make sure it goes through this router and to the internet, right, or at least to here so I can fill up this pipe, then I want to send it to a destination IP that exists somewhere over here. Okay. If I send it to this destination IP, well, I'm going to be sending traffic to this pipe, this interface, and maybe do some stuff to this PC, but I'm not going to be filling up this. And again, when you fill up this, it affects the whole site. not just that PC. Okay. So what I've chosen is an IP address 203.0.113.1. Look up this IP if you're interested. This is not an IP that belongs to anyone. This IP address is known as one of the reserved IP addresses, where the Internet Authority of Internet Numbers, I can't remember the acronym, but the consortium that hands out IP addresses decided that there's a certain block of IPs they don't want to hand out to anyone. This IP falls in that range. So this IP is used for documentation specifically. So people use this in like their documents and training network textbooks and stuff, but it's not assigned to someone. And why that's important is because if I'm going to do this, I'm going to send a blast of traffic through. Now, it's not much traffic. It's like, in this attack, we're going to use like 40, 50 megabit per second of traffic. But I don't want that to go past here. I don't want it to end up on a web server. And the web server admin is like, hey, why are you trying to flood my server with ICMP traffic? Okay. This IP, because it is not an actual legitimate routable IP, as we call it, right? It doesn't have a route, meaning your ISP doesn't know how to get to it because it doesn't exist. The traffic will get through your home router, through the upload pipe to your ISP. The ISP will drop it, okay? Because the ISP has nowhere to send it. And usually what happens when you don't have a route is that you discard that traffic through something known as a null route. So the ISP will drop the traffic because it doesn't know where to send it. And it will end here. So really the only pipe that you're compromising is your own upload to the ISP. But again, this isn't something that you're going to do unless you have permissions, unless you have controls, unless you have a good test environment where you know that's going to happen. Okay. So that covers to where, right? We use this IP, which is a public IP, so that it goes through my modem to the internet, but it doesn't actually hit anyone because this doesn't exist. Okay. Now, the final one is from where. And now this is a pretty simple one, but you want to send it from a PC on the network with a network card faster than the upload rate. And I kind of illustrated that here, but to be clear, we want to be sending traffic out my network card on my PC or whoever the PC is at a faster rate than the pipe we're trying to fill. So if this was only a 10 gig network interface card, like if I was back in the 90s, and this was only, 10 megabit, then I'm not really going to be able to fill this with overflow this interface with traffic because I'm sending exactly as much as it can handle. So I'm likely not going to see any disruption at all. I want to have an interface that's faster than what I'm sending to. Most modern home internet has upload rates which are slower than 1 gig. Most. There are people with symmetrical fiber these days who have 1 gig up. This is not for you, or if it is, you can just find a PC, for example, with a 10 gig card and try it, okay? And allow that PC to generate more traffic than the 1 gig. But for most people in most countries across the globe, they have less than 1 gig of capacity, and that's what you need to have a network card on the network that can do more than the upload. So the other thing I'll mention is that you want to be doing this with a LAN connection. Okay, not a wireless connection. You can do it with wireless. It does work. However, you're more than likely to just kill your local wireless connection because your AP can't handle the traffic. Then you actually are going to get those packets to the ISP. So if you have a wired connection, that is all the better. So the next thing we're going to cover is I'm going to show you the tool. I'm going to show you how to test how much traffic is generating. And then we're going to wrap it all up and show you the attack. So to get ready to do the attack, before I actually do the full attack, I want to show you how nping works and then show you how to test how much traffic nping is actually generating. Because nping, like most packet generators, they're not going to be able to, or you're not going to be able to enter like, I want 100 megabit per second of traffic. I want 200 megabit per second of traffic. It's going to give you like a packet count or a rate. And then you're going to have to play with it to see how much it's generating to make sure, like we mentioned a few times, that the actual rate you're sending is greater than the interface you want to overwhelm. So here's a command in front of you, okay, with a few modifications that we're going to get to. So nping -- ICMP to make it ICMP ping, -- destination IP, and I've set an IP address here. I'll get back to this in a sec, but this is your target. Data length is just the packet length. You can leave this out if you want, but this ensures that pings are the full size packet and not just 64K. So I would definitely do this, but if you left it at default, it would be smaller packets and therefore smaller throughput. And the rate I've set to just a really big number, and the count is a really big number. Rate is how many packets you want to send per second, and count is just the total number of packets you want to send in this one command. Okay, and I just set it to a ridiculously high number. Now, what you want to be doing is testing this to see how much traffic is going to get generated. So before you actually unleash it on an actual interface, what I like to do is set the destination to an IP address that's not used. Okay, so in this case, I know for a fact from my network that this 10.0.10.99 is not used by anything. And you want to start with rates and kind of go up, from a low end to a high end, just to see where the sweet spot is. Because at a certain point, the application is not going to be able to go faster, and you want to know like what that kind of terminal rate is, right? So what I'm going to do is start at a rate of 1,000, and I'm going to hit enter. Now, why I have this screen up here is that this is going to show me in real time the input and output from my network card, so I can assess roughly how much traffic is being generated. So let's see it live. Hit enter. You can see here all the packets are being generated and sent out. And right away, you can see my send has spiked up to about 8.4, 8.5 megabits per second. You can see the graph is actually reflected as well. So I can tell myself, okay, well, 1,000 or rate of 1,000 means approximately 7.7 megabits per second of traffic being generated, which is not enough for our example, because if you remember, as I mentioned multiple times, you need to have it more than the destination that you're trying to overwhelm. So let's stop that. Stop. And I'm going to turn my rate up. You can see immediately the traffic goes down because I'm not generating anymore. My send goes down to just a few kilobits per second. Let's turn that up to, say, add 2 more zeros. I don't know what the number is, but let's just put that in and see what happens. And now we're at about 34 megabits per second. That's pretty good, right? Now, for my application, my home internet only has 10 megabits per second up. That's totally fine, right? This will be fine for that. If you have higher upload speeds, your location, then you want to actually try to max this out so you get higher and higher rates to go over the threshold, right? So let me keep adding zeros to see where we end up, right? I'm going to just add a bunch of zeros in there and see what happens. At a certain point, you're going to hit a max rate for the application, not a max rate for the network card, but max rate for how fast this application can push out on this operating system. Okay. Now it looks as though we're hitting about 30 megabits per second, right? Which for some of you may not be fast enough for your internet connections. The good thing about nping is what you can do is kind of add them up, right? So I'm going to have another terminal here. This one's kind of going and doing its thing. Oh, everything disappeared. Where did it go? There we go. So one of these is going. I'm going to run the same command in this other window. Just bear with me here. So I'm going to copy this, paste it here, run it here, run it here. And what should happen is you can see the traffic starts to increase more. We're hovering now about 50 megabits per second. So you can overlay these, like if I went and got another one and ran that too. Over time, it should increase to a point where you're basically maxed out what this tool can push. Yeah, we're going up to 60 now. It's going a little bit higher. Perfect. 65. Awesome. Now, there are other ways that you can modify nping to push more data. You can play with the settings, play with the packet size, play with all that kind of stuff. But for me, for this attack, for my environment, this is fine. And if you want, again, you can play with nping to find the sweet spot for your network. All right, so let's bring this all together. Up here is the task manager for my PC. The PC in question is this PC here. So just any PC on the network that's not the script-kiddie PC. I'm using this to illustrate the performance degradation that happens when you actually run this attack. And then in the terminal below, this is actually script-kiddie PC. Okay, so script-kiddie PC is going to run this command, and then we're going to observe what happens to the blue PC. Now, the other thing I'm running is just a continuous ping to Google in the terminal from my blue PC, just to illustrate and show you visually what happens when this attack starts going off. Okay, so we'll let that keep running. So from script kdpc, it's the same command as before. Now I'm going to replace the IP address 10.0.10.99 with that public IP address that is non-routable, the 203.0.113.1, and hit go. And look at that. Traffic starts to dip. Now you may see stuff bounce as the server tries to react to what's going on, but right now that bit rate, the throughput, is getting choked. Okay, if I actually look at my pings, take a look at this. The pings have almost stopped. The latency is now, before, latency was in the 8 milliseconds, 9 milliseconds, 10 milliseconds. Now we're up to 1.3 seconds, 2.6 seconds, 3.1 seconds. And the transfer rate really hasn't recovered. That is the attack, right? At this point, even though some data is getting through, the download is effectively coming to a halt, right? You're getting little bursts here and there. And if I wanted to, I could ramp this up, right? I could open up another terminal to the Linux machine. And we'll do the same thing. Let's keep an eye on our pings. Pings are still timing out. You're getting severe packet loss through there, right? We're getting some data in bursts. Let's try to make this a bit worse. So what I'm going to do is I'm going to come over here. I'm going to stop this quickly. I'm going to copy this command over. Take it over here. Run it on here too. Now I'm running it on two different PCs. You can see as I stopped that command, the connectivity recovered back to about 54 megabytes per second or megabits per second. And now we're down flatlining again, right? We're getting little bits of data in and out. My pings are still failing like crazy. And this network is going to be effectively unusable at this point. So you can see there's a little bit of sign of life, but ultimately, if you're trying to use this for any sort of application, especially if there's multiple users on this network, it's not going to work. So that is the attack. It's fairly simple. It involves a very simple tool that anyone can download. And that's why ultimately it's so dangerous, is because it could be used by anyone who has access to install Nmap on their computer with an Ethernet connection to your network. So the last thing I'm going to do is talk to you about what do you do to actually prevent this from happening. All right, so let's talk about prevention. So again, the real problem here is that you have a limited amount of upload, right? Usually you have less upload than you do download. So it is a smaller pipe, so to speak, and anyone can use it on the network, right? So any PC who has access to your internet can upload data, can send pings through, just like we did. So it could be dangerous, right? So what do? You can't just block all internet connectivity to everyone, because then you're not going to be able to use the internet. So if you're in a home setting, the real security to this in a home setting is just to make sure that your home network, is secure, right? Don't let people onto the network. And usually what that means is don't let people onto your Wi-Fi. It's very rare that someone's going to walk in and like plug their PC into your router. You're not going to know about it at home. Okay. But if you have like Wi-Fi with a weak password, or you're not using WPA2 protocol, or you lend out your password, you have lots of guests on your network, anyone can do this who accesses your network. Okay. So that would be the number one thing if you have a home network, is just control very carefully who has access, and if you have wireless, secure it with a very, very strong password and very strong protocols. Okay. If you are in a corporate scenario or any sort of enterprise scenario where you can't easily do that, because maybe you might have hundreds of thousands of users, and certainly more than that of devices on the network, right? There's a few things you can do. One is that you can block ICMP outbound on your firewall. Okay, that would help with ICMP attacks. You can also do that for UDP as well. Some organizations will only allow things like HTTP 443 through the firewall. Some organizations use proxies instead to access the internet as opposed to that, and you just block off the firewall to only allow the proxies through. That's an option as well. The other thing that a lot of organizations do, if you can't block things off totally, is add a QoS profile to the firewall. So QoS stands for quality of service. And what quality of service does is it defines certain limits for types of traffic. Meaning, if you want to send TCP traffic on this port, you have 20% of the bandwidth. And if you want to send video traffic, you get 30% of the bandwidth, but you can't get more. So what that does is it puts traffic into specific categories such that if that traffic tries to exceed it, you're not going to be able to get over that. Like, it starts discarding the traffic. So therefore, that traffic is not going to be able to impact the whole pipe. It's only going to be able to impact its own category, so to speak. That's a good option as well. The other thing I would mention is that if you are in an enterprise scenario, you should really have a solution locally on the machines that are in your enterprise to control what can be installed on these machines. Like, this is just one tool, and Nmap is very ubiquitous. Like, it's actually available in a lot of corporate settings for people to do troubleshooting. But with Nmap comes a package generator that can be used to DoS, small internet connections. It could be used to DoS, say, branches. Like, say you have a corporation that has a lot of like satellite branches, and usually those branch connections are very small capacity connections because they're very expensive to have more. You can very easily overwhelm those connections with just traffic. And it could just be any random user, like, Joe Blow, who works in DevOps, could be fiddling with some new script on their PC and just knock over, all of your branches in like half the country, right? It's very, very easy to do. So some kind of solution on the PCs and on any asset to control what can be installed is very crucial in the enterprise setting as well. The final thing I will say is that you want to have some kind of mechanism to control what PCs are allowed on the network. Okay, so that we usually call that network access control. And effectively what that is that when you plug a PC into the network, there has to be some form of authentication between the PC and the local switches to say this PC is a registered PC or a permitted PC on the network and has access to get an IP address and access to send and receive data, etc. This is incredibly important. Otherwise, you could, for example, put all sorts of protections on the PCs that you own to prevent people from installing stuff. But if some vendor decides to come in, or some nefarious actor, and plug their laptop into a switch port, and they are able to get an IP and do whatever they want to do, then they can actually do the same thing and DoS your network from inside, either intentionally or unintentionally. Okay, so those are some of the techniques that, if you are in the opposite shoes, like if you're actually on the receiving end of this, or you want to prevent this from happening in your organization, those are the things that I would recommend first to prevent this kind of thing. That's it for this video. I hope you found this video useful. If so, please like and subscribe. Also, if you have an issue that you're working on and you would like to review the capture on the channel or get some advice, feel free to post a link to it below with the description, and I'll get back to you as soon as I can. Until next time.